Hi, in this video we're going to be talking about monotone and bounded sequences, and why we care if something is monotone and bounded. So we have a bunch of definitions, so we're just going to make a chart with all of these things. So a sequence is strictly increasing if for every n greater than some number n, so we're looking always at the tails, a n plus 1 is greater than a n. So the next term in the sequence is bigger than the one before it. But we can put a weaker condition on it. We can say that it's just increasing, and that's if a n plus 1 is greater than or equal to a n. And we have the same concept for strictly decreasing and decreasing. So it's strictly decreasing if the next one is always less than the one before it. And it's decreasing if it's less than or equal to the one before it. Now something is monotone if it's increasing or if it's decreasing. Okay? And it's bounded above if there is an m, some sort of real number such that an is less than m. This is for every n. So every number, every part of our sequence has to be less than some number. And it's bounded below if there is a number where an is greater than that number. And these can be different numbers. Something can be bounded above and below, and in that case, we say that it's just bounded, if it's both above and below. So why do we care if something is monotone and bounded? Well, if a function is monotone and bounded, it gives us just the right conditions to conclude that it converges. Now, it's important to note that it's not necessarily true the opposite way. So if something converges, it isn't necessarily monotone. Enter the ever so cleverly named monotone convergence theorem, which says that if a sequence is monotone and bounded, then it converges. So now let's look at a couple of examples of sequences. We'll see if they're monotone, we'll see if they're bounded, we'll see if the monotone convergence theorem applies, and we'll see if they converge even if the monotone convergence theorem does not apply. Let's start with the sequence negative n squared. So this looks a lot like negative x squared. So it's going to look like this guy as we approach infinity, or as we graph it. So as we approach infinity, it doesn't look like it's going to converge. So let's take a look and determine if it's the monotoneness or the boundedness that makes it fail, or if it's neither at all. So we know that negative n squared is not bounded below. Right, so if we were given any number, say k, we know that eventually negative n squared will be less than k. So it's not bounded below, and that tells us that it's not bounded at all. Now let's check to see if it is monotone. Checking if it's monotone isn't quite as easy, but it is in this case. So we just need to check if n plus 1 squared is that less than, greater than, or equal to negative n squared. So is it? It looks like it is from our graph, but let's just make sure. So we'll take this and we'll FOIL it out. So n squared plus 2n plus 1. And here we just have negative n squared. So we'll get negative 2n minus 1. And we're going to see how that relates to 0. And negative 2n minus 1, since n is always a positive number, this is always going to be a negative number. This guy right here is always going to be negative. So that tells us that's going to be less than 0. So yes, and a sub n plus 1 is always less than a sub n. So this is strictly decreasing, which implies that it's monotone. So monotone, yes. Bounded, no. All right, let's take a look at our next example. Negative 1 to the n plus 1. And we'll look, we know that it doesn't converge because we did the a sub 2n and a sub 2n plus 1 test. But we don't care too much about that right now. We just care if it's monotone and boundedness. So we know it doesn't converge. Let's check to see if it's monotone. Okay. Now if it's monotone, we're going to look at a sub n plus 1, and it's going to be less than or equal to a sub n, or a sub n plus 1 is going to be greater than or equal to an. Well, if n is even, then a sub n plus 1 is going to be equal to negative 1 to the 2k plus 1, and that is going to be odd, so that's going to be negative 1. And that says that an is going to be equal to negative 1 to the 2k, and that's going to be even. So negative 1 is less than 1. So if n is even, it is always less than. But if n is odd, then a sub n plus 1 is actually going to be 1, and a sub n is going to be negative 1. So 1 is greater than negative 1. So depending on if it's even or if it's odd, it switches from less than to greater than, less than to greater than, less than to greater than. So this is not monotone. Okay. So now let's check for boundedness. If we look at the sequence, we write out the first few terms. We have negative 1, 1, negative 1, 1, and so on. So our function, or our sequence rather, is always changing between negative 1 and 1. So it's bounded below by negative 1, or technically any number less than negative 1. And it's bounded above by 1 or any number greater than 1. And this tells us that we have a bounded sequence. So it's bounded, it fails monotonicity. Okay, let's take a look at our next example then. 3 over n as n ranges from 20 to infinity. So let's look at boundedness. Okay, if we look at our sequence, we have 3 over 20, 3 over 21, 3 over 22, and so on. So this looks like it's decreasing. And in fact, let's go down and take a look at monotonicity. So if we look at 3 over n plus 1, we want to compare that to 3 over n. Now n plus 1 is always greater than n, so when we take its reciprocal, n plus 1 is 3 over n plus 1 is going to be less than 3 over n. So this is monotone, and in fact it's monotone decreasing. And if it's monotone decreasing, it's going to be bounded above because it's going in a downward direction. So it's bounded above by any number greater than 3/20. And we can see that it's bounded below by 0. And to see this, we're just going to set 3/n equal to 0. And we know that that can't happen because then n would have to be a number. And that's not the case. And in fact, we get that 3 is equal to 0, which can't happen. But what if we pick another number? So say 3/n, maybe we'll pick, I don't know, negative 3/2. Any number you want. -1 might work a little easier for us. Well, that tells us that n would have to be equal to -1/3, or it would have to be greater than -1/3, which are, or my apologies, less than -1/3, which can't happen because n starts at 20 in this case and goes all the way up to infinity. So this can't happen. So it's bounded below by 0, bounded above by 3/20. It's monotone decreasing. And so the monotone convergence theorem tells us that this converges because it's monotone and it's bounded. And intuitionistically, that's a word, intuitionistically, this looks like it goes to 0, and it in fact does. So it converges to 0. Let's take a look at our next example, n/n+1, as n ranges from 1 to infinity. So let's first see if it's monotone. Okay, and we could compare n+1/n+2, and we'll see how that relates to n/n+1. But this could get a little tricky, and we'd be doing a lot of algebra tricks. Fortunately for us, we've taken calculus. So to compare these, let's just take the derivative. So we'll let f of x equal x/x+1. And we'll take the derivative of x. So it's going to be the bottom times the derivative of the top, so x+1, minus the top times the derivative of the bottom, so that's minus x, over the bottom squared. And so this gives us 1/x+1 squared. And that's always greater than 0, especially on our interval from 1 to infinity. There's some issues at x equals -1, but it's not even in our domain, so we don't even have to worry about it. So this tells us that f of x is strictly increasing. And that tells us that our sequence is strictly increasing, which tells us that it's monotone. Now, if it's monotone and it's increasing, it's automatically bounded below. We start somewhere and then we keep going in an upward direction, so there has to be a bottom one. And what's it bounded below by? The first term, or anything less than the first term, which is n starts at 1, so it's bounded below by 1/2. Now, is it bounded above? Well, let's take a look at the sequence again. Well, we know that n is always less than n+1. And that tells us that n over n plus 1 is going to be less than 1. And that tells us it's bounded above by 1. So yes, it is bounded. And the monotone convergence theorem tells us that since it is monotone and it is bounded, it must converge. Must converge. And we know what the limit of this is. It converges to 1. For our next example, let's take a look at n cubed over n to the 4th plus 100, as n ranges from 0 to infinity. So just as before, we could take a look at the derivative and see if there's any turning points. So let's just let f of x equal x cubed over x to the 4th plus 100. And that tells us that f prime of x is going to be equal to something over x to the 4th plus 100 squared. And what's the numerator? So it's the bottom, x to the 4th plus 100, times the derivative of the top, 3x squared, minus the top times the derivative of the bottom. Okay, the bottom is always positive, so we don't even have to worry about that. So let's just look at the top. So that's going to be 3x to the 5th plus 300x squared minus 4x to the 6th. And we want to know, when is that equal to 0, if ever? So if we do this, we get x squared that we can factor out. And on the inside, we're going to get negative 4x to the 4th plus 3x cubed plus 300. And that's going to be equal to 0. And what we can now do is use the quartic formula or some other algebra system or some other method of figuring this out, because this is quite a monster of a problem to solve. But we know that x is equal to 0, and I will be right back with our possible x's, if any. So x has two possible values. So x could be negative 2.7718 approximately, and x is approximately 3.1499. And this guy right here is going to be the one that gives us trouble. So this tells us that between 3 and 4, it might change direction. So let's go ahead and make sure it doesn't. So we'll pick 3.1499. Let's pick a point to the left a bit between 0 and that, say 1. And then we'll pick any point greater than that, say 10. So if we look at f prime of 1, we just need to concern ourselves with the numerator. So is it going to be greater than or less than 0? And x squared is always greater than 0, so we have negative 4 plus 3 plus 300. And that is greater than 0, so it's increasing on the interval from 0 to, in our case, 3. And then if we look at f prime of 10, well, we have negative 4 and then 4 zeros plus 3,000 plus 300, and those can't overpower the negative 40,000, so it's less than 0, so it's decreasing on this interval, which tells us that is in fact not finally, let's check to see if this sequence is bounded. And to do that, we're going to let f of x be equal to x cubed over x to the fourth plus 100, the continuous analog of our sequence. And let's take f prime to see where it's increasing and decreasing and go from there. So we know what f prime is. F prime is going to be this guy here. So let's just copy that and move it down here. Okay. And we know where it's increasing and decreasing as well. So we have our 0 here, and we have, what was it, 2 or 3.1499. So 3.1499. It doesn't really matter what's going on over here because remember we're going out towards infinity. Let's just make this a little less straining on the eyes. And then we know that it continues decreasing at this point. So if f of x is bounded, then our sequence is bounded. So we know that it's increasing and then decreasing. So we claim that it's bounded above. Okay. And that's because there's going to probably be a turning point here. So let's go ahead and plug in f of 3.1499. And that is equal to approximately 0.157. So we can say that this is bounded above by, let's say, 1. Just to be safe, we'll just pick any number bigger than 0.157. It was an approximation, so our answer was also an approximation. So let's just play it safe and go with 1. Now, to see if it's bounded below, we're going to have to analyze the function itself. So we have x cubed over x to the fourth plus 100. And we're looking at as x goes from 0 to infinity. So as we go out towards the end part here, as we look at our tail, x to the fourth overpowers x cubed. So this thing, it looks like it's going to 0. So we just need to check to see if it is positive or if it ever hits 0. So we say x cubed is equal, well, x cubed over x to the fourth plus 100 is equal to 0. And at this point, we get that x is equal to 0. So we have that our sequence crosses the x-axis or goes negative at 0, which is our starting point. But then it's increasing, so it becomes positive, and then it decreases, so it becomes negative, but never touches 0 again. So we can say that it's bounded below by 0. And that tells us that we have a bounded function, or a bounded sequence, that is not monotonic, but it converges anyway. Because if we were to take the limit, that converges to 0. So taking the limit as x goes to infinity of f of x, we get 0. Any questions, comments, or concerns, you can place them in the comments below. And as always, thank you for watching.